Hey everyone, welcome back, and today let's solve Leetcode problem 1760 titled Minimum Limit of Balls in a Bag. So we're given an integer array nums where the ith bag contains nums at I balls, and we're also given an integer max operations. So we can perform the following operation at most max operations times. So we can take any bag of balls and divide it into two new bags with a positive number of balls. For example, a bag of 5 balls could become two new bags of 1 and 4 balls. Or another way we could distribute them would be two new bags of 2 and 3 balls each. So the penalty is the maximum number of balls in a bag, and we want to minimize your penalty after all of the operations, right? After all the max operations are actually been completed, and we need to return the minimum possible penalty after performing the operations. We want to minimize that actual maximum number of balls in a bag. So in example 1, we have our input array nums to be just one bag of length 1, and that's going to have 9 balls. And the number of operations we have to do, the max number of operations, is going to be simply just 2. In this case, we have to output a value of 3. And the reason why is because we can first divide this bag into two different bags in this array, one of 6 and one of 3. Then we can divide the 6 into two more bags, 3 and 3. And the bag with the most number of balls is 3. And that is the minimum penalty we can have. Right? We can't have any smaller values here to minimize the penalty. This is the minimized basically maximum number of balls in any bag. It's going to be 3, right? We can initially split the 9 into 6 and 3, and then split the 6 into 3 and 3, and another 3. And the maximum number of balls, or the minimized penalty, is going to be 3. So in example 2, we have our input array nums to be 2, 4, 8, 2, and our max operations to be equal to 4. In this case, we have to output 2. Why is that? Well, we can first initialize, or rather divide this biggest bag here, 8, into two different parts, right? We can split them each 4 and 4, right? And then we get 2, 4, 4, 4, and then 2. And then we can divide it with we can divide this bag, the 4 bag, into two more slots, right? The biggest bag then becomes two more 2s. And then we get the next biggest bag. That's going to be this 4 here. That's another 2s. And then we divide this next biggest bag, 4 here, two more 2s. And then we have all 2s. It's spread out equally. And this is the minimized maximum number of balls in any bag. And that's going to be an output of 2, right? So a quick observation you can make here is that we're looking for this biggest bag here. And we're effectively, essentially halving it, right? We're kind of distributing it as equal as possible for the other two bags, right? Because that's going to actually help us minimize our maximum possible penalty. Okay, so with that out of the way, I will give you guys a few seconds. I'm going to just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're actually going to be using the binary search algorithm. And we're going to do this to basically efficiently find the smallest possible value of all the balls, or rather balls in any bag, right? And our goal effectively is just to determine the smallest integer value x in the range such that by splitting the balls in the bags, no bag has more than x balls. Right? And the main thing that you kind of have to take away from this solution is that we can simulate this process. It's kind of a simulation problem by effectively just checking whether a given x in that corresponding binary search range at that iteration, if it's feasible using at most the allowed permitted number of operations, max operations. Right? And we can have a helper function to help us check that. Right? And so we're going to have a function, I'm just going to call it can divide or whatever, right? It's going to be a helper function, and it's going to take in a parameter mid as an index that actually checks, can we split the balls such that no bag has more than mid balls, right? And we're going to do this by simply just iterating over the range of the possible values for x using that binary search algorithm, right, where the search range is 1 through the max of our input array nums, and the result is going to be, of course, the smallest value of x that actually satisfies that condition. So with that out of the way, let's go ahead and dive straight into code here. So I'm actually going to directly just initialize my helper function here. I'm going to call it can divide here. Right? And it's going to take in a parameter mid, right? where this mid in this iteration of this parameter, it's simply going to be the potential maximum number of balls in any bag that we're actually testing at that iteration of our binary search to see if it can divide, if it's actually a feasible value to actually use. Okay, now that we've actually initialized this helper function, now let's actually initialize the number of operations that we're going to be using. It's going to be initialized to 0. Right? This is simply going to just count how many operations we actually need to make to split the bags, just so that no bag actually exceeds the number of mid balls, right? Now let's actually iterate over our input array nums. So for every num in our input array num, simply iterating over all the different elements, we want to increment our operations by num minus 1 integer divided by mid. And what does this actually mean here? Well, for each bag in input array nums, we simply have to actually calculate, well, how many operations are actually needed to make sure that the number of balls in the bag is at most going to be mid, right? And num minus 1, let me actually just space this out. And num minus 1 divided by mid, this is just quick order of operations here in Python, using these parentheses, it's going to give us the number of splits that we actually need, because each split is going to reduce basically the size of the bag, right? Each split is reducing the size of the bag, and we're dividing that by mid. It's going to actually give us the number of splits needed for the number of operations, right? And effectively, now we have to check, well, is the number of operations, so if that's greater than max operations in this iteration, then we immediately have to return false, because that's effectively just breaking the rules of the problem. I don't know why my typing skills are so bad today. Return false, right? Because that's basically telling us if at any point in this iteration, if the required operations we need to have at most mid balls, if that exceeds the max operations that we're allowed to have, that's our second input parameter, that means that this mid value in this iteration for this helper function, it is not feasible. We have to immediately return false. However, if we don't return false in this for loop here for any iteration for this mid value, for the number of operations we need, we can then return true after. Right? That's simply just telling us that we can actually finish this loop without actually exceeding the max operations input, and that means that this mid value is actually going to be allowed. It's going to actually be feasible for our input array nums. Now let's actually initialize our binary search range here, like we usually do for binary search problems. Right? I'm going to have my variables left and right to be equal to 1 and the max of our input array nums, right? Left is going to be the smallest possible value for the middle, and right is going to be the largest number of balls in a single bag in the worst case scenario. Okay, now that we've actually initialized this binary search range, now let's initialize our result to be starting at right. Right? This is going to be the result, and we're going to initialize it to right. It's going to be the worst case scenario where no splits are actually made. It's starting at the max of our input array nums, and we're going to keep decreasing it for that actual iteration in every binary search range. Now let's have our standard binary search while loop here. So while left is actually in bounds of right, so while it's actually less than or equal to our right index, right? So effectively, while these left and right pointers actually meet, we're going to actually perform binary search, right? So we're going to initialize mid to be equal to left plus right divided by 2, the actual middle value, the definition of mid, right? It's simply going to be the middle value of the current range, but that's between left and right to whatever values there are in this iteration. And now if can divide at mid, and technically I could do equal to true. This is simply kind of like a quicker way to do it in Python. This basically checks, well, is it true or false based on its Boolean value evaluation, right? And if can divide is actually true at mid, right, that basically checks, well, is it actually possible to split the bags such that no bag actually has more than mid balls, that we're using this can divide helper function to actually check. Well, if that's the case, then we want to update our result to then be mid, and then set right to then be mid minus 1. Right, we want to now search the left size of this binary search range. There's no point in going to the right size. We want to increment right, or rather update right to be mid minus 1 to go to the left range of this search, right? Because we know that we can successfully divide mid using this can divide helper function. We know that we can actually possibly split the bags such that no bag has more than mid balls. And so we can then increment or rather update our result in right, worst case scenario, and actually start looking in the left search range, right? Right, so again, if this is feasible, we simply have to just continue searching in the smaller range. Now, if that's not the case though, so else, If can divided mid is not true, then we have to increment our left variable and set it equal to mid plus 1. So this number of mid balls is already not feasible. We need more balls at least to actually make it feasible so that no bag has more than that. And so we then have to increment our left, or rather update our left to be mid plus 1 to search in the right half or the right range of this current iteration of basically the larger range of left equals mid plus 1. Right? Because we know we need more than mid balls for it to actually be feasible, for us to actually have enough balls. Right? And effectively, we simply have to return the result to whatever mid value or number of balls it actually is, right? It's going to be the smallest feasible value of mid as a result. That's going to be stored in result. So unless I made any syntax errors here, this should be accepted and this should be a valid solution. So let's go ahead and check if it works. And as you can see, this is just about as efficient as you can get. So for a quick high-level rundown here of how this code actually works, effectively, we're actually using the binary search algorithm here in this portion of the code here to actually find the smallest possible value of x, or mid, such that we can actually split the balls in the bag to satisfy the given conditions, right? And we're going to use this helper function here to simply just check, well, is the current value mid, number of balls, is that actually a feasible option, right? If no bag has more than mid balls, right? And we're simply just checking the feasibility of this function, again, using that can divide helper function, and we're narrowing down our search range incrementally, right? So simply just kind of splitting it in half based on whether the current value mid, if it actually works or not, if it's actually feasible or not. So for the time complexity of this solution, this is going to be a big O of n times the log of the max of our input right now. So I'm going to actually explain that before I do that. I'm actually going to comment that out. So the runtime, oops, I don't know why I have caps lock on. Runtime, actually, let me go like that. Complexity is going to be equal to the big O of n times the log of the maximum value of our input array nums. But why is this actually the case? Well, let's break it down into its simple subproblems here. Well, for each value of mid, right, we have to actually iterate over all the different bags in nums, right? That's going to be a linear time operation. This can divide helper function that we actually use to apply to mid for every iteration of this binary search range, it's going to be a big O of n, or linear time operation. Why is that? Well, because we're actually iterating through all the different bags, or num, in our input array nums. Right, that itself is a big O of 1 operation, or rather a big O of n operation, because it's a one-pass kind of operation, right? We have to actually iterate over all the different characters exactly once of our input array nums, right? And the binary search is going to run in big O of log times the max of nums, right? It's simply just a logarithmic operation or algorithm. That's why it's considered to be very optimal. So the overall time complexity is going to be that linear time part, so n times the log of the max of nums. That's a binary search algorithm contribution runtime complexity, right? And for the memory complexity, believe it or not, this is actually as optimal as you can get it to be. Memory complexity, this is simply going to be big O of 1, right? Why is that? Well, we're not actually using any auxiliary memory here. We're not using any extra data structures to actually store any elements from our input. We're really just using a few integer variables like operations, left and right, and result, of course, as well. But we're not actually using any extra data structures, unlike simply just integer variables. So for that reason, this is going to be a big O of 1, or a constant time solution that does not grow exponentially or anything like that with our input size for all the different test cases. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.